Reality itself might be built upon a turbulent sea of chaos. This is the quantum foam, a hidden layer of spacetime that defies everything we think we know. By the end of this, you will see the entire cosmos in a completely new way. We will uncover how this microscopic frenzy could be responsible for the birth of black holes and might even hold the secret to the universe's final fate. How could something so small dictate the destiny of everything so vast? Even the most perfect vacuum is not what it seems. If you could shrink down to an almost impossibly small scale, a realm so tiny it defies ordinary measurement, you would witness a scene of pure chaos. This is the Planck length, a size so minuscule that our current laws of physics simply break down. Here, the smooth, predictable fabric of spacetime predicted by Einstein shatters into a seething, turbulent froth. This is the quantum foam. Think of the calm surface of a pond. To our eyes, it appears still and continuous, but if you could peer into its molecular heart, you would see a frantic dance of particles in constant, turbulent motion. The quantum foam is the very fabric of our universe experiencing that same kind of frenzy. It is a bubbling sea of potential, where microscopic wormholes and virtual particles spontaneously flash into existence for mere fleeting moments before vanishing back into the energy from which they came. This revolutionary idea was first proposed by the physicist John Wheeler in the 1950s. He realized that the marriage of quantum mechanics and general relativity meant that empty space could not be truly empty. Instead, it must be a dynamic, foamy substance, its geometry constantly fluctuating. This foaminess implies that spacetime itself has a discrete, grainy texture, much like a digital photograph that appears smooth from a distance but is actually composed of tiny pixels. This single insight has monumental implications. It suggests that the very stage upon which the cosmos plays out is not a fixed and smooth backdrop, but is alive with microscopic turbulence. To understand this chaotic foundation is to take the first step toward the ultimate goal of physics, a unified theory that can seamlessly blend the world of the very small with the force of gravity that shapes the very large. The journey to this profound idea, however, began long before Wheeler gave it a name, rooted in a fundamental conflict between two pillars of modern science. Einstein's vision of a smooth, geometric cosmos was a monumental leap in understanding, yet it clashed profoundly with the strange new world of quantum mechanics, where certainty dissolves into a dance of probabilities. This was the central conflict of 20th century physics, a fundamental schism between the force that governs the stars and the rules that rule the atom. One brilliant mind saw this not as an impasse but as a gateway. John Wheeler looked at these two competing descriptions of reality and asked a revolutionary question. What if the smooth fabric of spacetime was an illusion, a kind of cosmic mirage that only appears continuous from our macroscopic vantage point? He proposed that if you could peer down to the universe's smallest possible scale, the Planck length, you would find that the serene stage of Einstein's relativity vanishes. In its place is a seething, chaotic froth. Wheeler called this the quantum foam. To visualize this, he offered a powerful analogy. Picture a stormy ocean viewed from high in the sky. From that great distance, the sea appears as a single, smooth, glimmering surface, but descend lower and you see the waves, the churning whitecaps, the violent, turbulent motion that constitutes its true nature. The quantum foam is that underlying turbulence for spacetime itself. At this unimaginably tiny scale, the geometry of space and time is not fixed. It warps and twists randomly. Microscopic wormholes blink in and out of existence. Virtual particle pairs spontaneously emerge from nothingness, only to annihilate an instant later. This relentless activity is the very essence of empty space. Wheeler's profound insight was that this foamy structure might be how gravity itself becomes quantized. Just as light is composed of individual photons, the gravitational field might be composed of these fleeting, dynamic fluctuations in the fabric of spacetime. His vision laid the entire foundation for the modern quest to find a theory of quantum gravity, suggesting that the key to uniting the cosmos lies in understanding its chaotic, pixelated heart. To truly grasp this chaotic foundation, we need to explore the core principles that make such a bizarre reality possible. The Planck scale is a world of numbers so small they defy human intuition. A Planck length is 10 to the negative 35th of a meter. To put that into perspective, if you enlarged a single atom to the size of the entire observable universe, a Planck length would still be no larger than a single tree on our entire planet. Time at this scale is equally alien. A Planck time, the interval it takes light to cross that tiny distance, is a mere 10 to the negative 43rd of a second. This is the ultimate basement level of reality, the final frontier where our understanding of physics hits a wall. At this scale, the force of gravity, which seems so weak in our everyday world, becomes as powerful as the electromagnetic and nuclear forces. This is the point where Einstein's smooth, geometric universe collides head-on with the chaotic probability of the quantum world. The energy fluctuations here are so unimaginably violent that they do not merely exist within spacetime, they actively twist and warp the fabric of spacetime itself. This is the engine of the quantum foam. These violent fluctuations are not gentle ripples. They are spacetime tsunamis, creating a seething landscape where virtual black holes and wormholes spontaneously erupt into existence. These are not the stable black holes formed by collapsing stars. They are fleeting gravitational pits, appearing and vanishing in less than a Planck instant, their brief lives a direct consequence of the foam's inherent chaos. This realm is, for now, a place we can only visit in theory. Our most powerful particle colliders cannot even come close to probing these energies and distances. It is like trying to study the texture of a single grain of sand with a telescope trained on a distant galaxy. So how can we possibly know this foam exists? Our only path is through the brilliant, indirect observations of theoretical models and the subtle fingerprints this chaos leaves on the cosmos we can see. This relentless churning is not random noise, but a fundamental process dictated by one of quantum mechanics' most profound rules. Heisenberg's uncertainty principle tells us that on the tiniest scales, the universe operates on a kind of borrowed energy. For incredibly brief moments, the strict conservation of energy can be sidestepped, allowing something to emerge from what we perceive as nothing. This is the engine that drives the quantum foam. It continuously births fleeting particle and antiparticle pairs, and even microscopic wormholes that live for mere instants before vanishing back into the void. This is not a passive background, but an active, dynamic substance. The geometry of space and time itself is constantly writhing, a turbulent sea that influences everything that moves through it. The path of a single photon traveling across the universe is subtly jostled by this underlying graininess. The very expansion of the cosmos on the largest scales might be subtly guided by the collective churn of these smallest possible fluctuations. You can think of each of these turbulent events as an atom of spacetime itself. Just as all matter is built from atoms, the smooth, continuous fabric of the cosmos might be an emergent illusion, woven together from countless, chaotic, microscopic knots of energy. This inherent graininess is the active ingredient that makes the quantum foam so pivotal. It is the reason why empty space is not truly empty and why the stage of the universe can never be perfectly smooth. Future experiments hope to detect this fundamental fuzziness by observing how high-energy light from distant gamma-ray bursts travels for billions of years. Even the slightest turbulence in spacetime would leave a tiny, telltale fingerprint on that ancient light. This microscopic chaos is not just a curiosity, it is the very substance from which our reality may be constructed. So if this turbulent foam is the true foundation of everything, how exactly does it stitch together the smooth, vast universe we perceive around us? This microscopic turbulence does far more than simply exist. It actively sculpts the geometry of the cosmos. The continuous churn of the quantum foam means that spacetime itself is never truly at rest. Its fabric is constantly being stretched, twisted, and folded on the smallest of scales. This has a direct physical consequence. It means that if you tried to measure a fundamental property like the distance between 2 points with infinite precision, you would fail. The very act of measurement would be disrupted by the foamy texture beneath your tools. At these scales, the concept of a perfectly straight line loses all meaning. The path of anything moving through this seething foundation becomes inherently fuzzy. This foamy texture leaves its mark on the light that travels across the universe. A photon from a distant quasar, a journey spanning billions of years, does not travel a smooth, pristine path. It is perpetually jostled by the space-time fluctuations it encounters. Over these immense cosmic distances, this subtle jostling can accumulate. The effect is analogous to looking up at a star on a hot summer night. The star appears to twinkle because its light is passing through the turbulent layers of our atmosphere, bending and distorting ever so slightly. The quantum foam does the same thing, but on a universal scale. It could cause the images of the most distant celestial objects to appear slightly blurred or smeared. Our most powerful telescopes are now on the verge of detecting this cosmic blurring, searching for the faintest imprint of spacetime's graininess in the ancient light from gamma-ray bursts. The influence of this foam might extend to the very largest structures we see. Some cosmologists speculate that the initial seeds for the cosmic web of galaxies, the vast filaments and voids that span the observable universe, were planted by quantum fluctuations during the first moments of the Big Bang. These primordial ripples, amplified by inflation, could be the magnified echo of the quantum foam's relentless activity. This means the foam is not a passive stage. It is an active participant in cosmic evolution, its microscopic chaos potentially writing the blueprint for galaxy clusters and superclusters. This shaping power bridges the universe's smallest and largest scales, suggesting that the quantum foam's texture is woven into the fabric of everything we see. This dynamic environment is sustained by a bizarre quantum phenomenon, the spontaneous creation of virtual particles from the void itself. These ephemeral ghosts are the true substance of the quantum foam. Virtual particles are not mere mathematical tricks. They are the primary actors in the turbulent spacetime sea, borrowing energy from the vacuum's inherent uncertainty to flash into existence for the briefest of moments. Governed by Heisenberg's principle, a particle and its antiparticle partner can spontaneously emerge from what seems like nothing, living on borrowed energy and borrowed time before they are forced to annihilate and return their debt to the universe. This endless dance of creation and destruction is not happening on a static stage. Each pair that bursts into life generates a minute, fluctuating gravitational field, a tiny warp in the fabric of space that contributes directly to the foam's churning structure. This process is so fundamental that we can actually observe its consequences in a laboratory. Consider the Casimir Effect. If you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they will be pushed toward each other by an invisible force. Why? Because the narrow gap between the plates restricts the kinds of virtual particles that can pop into existence there. Outside the plates, a limitless sea of virtual particles can form, but inside the gap, only certain wavelengths are allowed. This imbalance in quantum pressure from the outside pushes the plates together, a clear, measurable effect caused by these so-called ghosts. Their influence extends far beyond laboratory experiments. The existence of Hawking radiation, the process by which black holes slowly evaporate, is also a direct result of virtual particles. Just at the edge of a black hole's event horizon, one member of a virtual pair might fall in while the other escapes. The escaped particle becomes real, carrying energy away from the black hole and causing it to lose mass over astronomical time. This demonstrates that virtual particles are not just theoretical, they have a tangible, physical impact on the cosmos. Within the chaotic environment of the quantum foam, these particles can do even stranger things. They might momentarily coalesce, their fleeting energy twisting spacetime into the form of a temporary wormhole or a microscopic black hole that vanishes almost as soon as it appears. These are not the stable tunnels of science fiction, but transient knots in reality's fabric, adding incredible layers of complexity to the vacuum. The constant activity of these ghostly particles is essential to the foam's behavior, and it is through their subtle fingerprints that we might one day confirm this hidden layer of reality. This relentless churn of particles and forces within the foam hints at an even more incredible possibility, that spacetime might be threaded with countless microscopic tunnels. These microscopic tunnels are woven directly into the chaotic fabric of the quantum foam. Wormholes, often called Einstein-Rosen bridges, are not just the stuff of science fiction, they are a natural prediction of our best theories of gravity. Within the seething foam, these are not the grand, stable tunnels that could carry starships. They are ephemeral structures, constantly snapping into and out of existence in a frenzied dance that lasts for mere fractions of a Planck second. They are as much a part of the vacuum's substance as the virtual particles themselves. In this transient state, they could serve as the universe's most fundamental plumbing. One profound possibility is that these tiny wormholes act as conduits for quantum information. When two particles become entangled, their fates are linked instantly across any distance. This spooky connection might be physically facilitated by a microscopic wormhole bridging the space between them, creating a tiny, temporary shortcut through the foam. This idea beautifully links the phenomenon of entanglement with the geometry of spacetime itself, suggesting that quantum weirdness and gravitational structure are two sides of the same coin. These fleeting tunnels could also, in theory, enable a form of time travel on the smallest of scales. A particle might briefly dart into one end of a wormhole and emerge a minuscule moment into its own past. This would not allow for paradoxes on a human scale, as the effect is confined to the unimaginably brief and chaotic Planck realm. The foam's constant fluctuations would instantly destroy any such time loop before it could influence the larger world. Beyond connectivity, these structures might play a vital role in holding spacetime together. Some theoretical models suggest that a dense network of worm lines, these microscopic bridges, could stabilize the foam's violent fluctuations. They could act like a web of tiny stitches, preventing the fabric of reality from tearing itself apart under the immense gravitational stresses at the Planck scale. They might even mediate fundamental forces, providing a hidden pathway for particles to interact. While the dream of traversing a cosmic wormhole remains distant, their existence in the quantum foam is a powerful clue. They hint that the universe's most intimate level is not just a chaotic storm, but a deeply interconnected network, where every point in spacetime is linked to every other by a web of transient bridges. This intricate network of tunnels leads our investigation to another, even more extreme structure that flickers within the foam. The most extreme gravitational whirlpools within this chaotic sea are not massive objects but microscopic, fleeting black holes. These are not the cosmic giants born from dying stars, but something far stranger and more fundamental. They erupt directly from the foam's most violent energy fluctuations, forming for less than a Planck instant before vanishing back into the turbulent vacuum. Imagine a stormy ocean where, for a split second, a tiny, perfect whirlpool spontaneously forms and then just as quickly collapses. A virtual black hole is a gravitational whirlpool in the fabric of spacetime itself. Stephen Hawking revolutionized our view of black holes by proposing they are not entirely black, but slowly evaporate by emitting radiation. This Hawking radiation, he speculated, would apply even to these transient virtual versions. Their entire life cycle, from explosive birth to quiet evaporation, is compressed into a timescale so brief it is essentially a single, violent event within the foam's ongoing churn. Their transient nature does not make them insignificant. Each one represents a point where gravity becomes so intense that the very concepts of space and time break down completely. Could the collective effect of countless such events subtly alter the fundamental rules that particles follow? Some theories suggest these microscopic black holes might cause tiny violations of quantum mechanics or act as the ultimate scramblers of information. If a particle interacts with a virtual black hole, even for an instant, the information it carries could be lost forever, or perhaps it is encoded into the Hawking radiation that remains. This touches upon the infamous black hole information paradox, a puzzle about whether information is truly destroyed in a black hole, which would violate a core tenet of quantum theory. Resolving this paradox might require understanding the role these fleeting gravitational pits play. They are not just curiosities, they could be the key to unlocking a theory of quantum gravity, revealing how the smooth force we call gravity emerges from the discrete, chaotic flicker of the quantum world. To make sense of such bizarre phenomena, we must turn to the mathematical architectures that try to tame this chaos. Capturing this chaotic foam in a set of mathematical equations is one of the greatest challenges in modern physics. Several brilliant, competing frameworks have emerged, each attempting to paint a coherent picture of this turbulent reality. String theory, for instance, proposes a radical shift in perspective. It suggests that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy. The frantic dance of the quantum foam, in this view, could be the result of these strings interacting with each other across multiple hidden dimensions, dimensions curled up into sizes far smaller than an atom. The foam's fluctuations might be the visible echo of these vibrations playing out on a cosmic scale. A completely different approach is taken by loop quantum gravity. This theory does not add extra dimensions, but instead focuses on the fabric of space itself. It proposes that space is not smooth and continuous, but is woven from a network of tiny, discrete loops. Picture a cosmic spiderweb where each individual thread is a fundamental line of gravitational force. Where these threads intersect, they create tiny, quantized packets of space, like the pixels on a screen. The quantum foam, then, would be the dynamic, ever-changing nature of this spin network, a seething digital tapestry that forms the basis of reality. Another fascinating method uses the raw power of computation. The approach known as causal dynamical triangulations builds spacetime from the ground up inside a supercomputer. It starts with an enormous collection of simple, geometric shapes like hypertriangles and allows them to connect according to specific rules. As the simulation runs, these countless simple pieces self-organize, and from their collective behavior, a four-dimensional universe with a foamy, fluctuating structure spontaneously emerges. It is a digital universe in a box, revealing that the smooth cosmos we know could be a statistical average of an underlying chaos. Each of these paths offers a unique window into the microstructure of spacetime. String theory provides a unified home for all forces. Loop quantum gravity gives us a compellingly simple picture of quantized space, and computer simulations show us how complexity can arise from simplicity. Yet all of them, in their own way, are guided by the same goal: to finally unite Einstein's gravity with the quantum world by deciphering the secrets of the foam. The ultimate test, however, lies not in their mathematical elegance, but in whether we can find any tangible evidence that this profound chaos is real. The sheer scale of this challenge is almost beyond comprehension. Our most powerful tools are blunt instruments next to the delicate, fleeting nature of the quantum foam. To directly observe its turbulent structure would require a particle accelerator the size of our entire galaxy, a machine of unimaginable power just to glimpse the universe's finest grain. Since that is impossible, scientists have become cosmic detectives, searching for the faintest shadows this chaos casts upon the light that journeys to us across the cosmos. One of the most promising clues lies in the light from gamma-ray bursts, the most violent explosions in the universe. When these colossal events occur, they send out photons of vastly different energies racing toward us. In a perfectly smooth classical spacetime, as Einstein envisioned, all these photons, regardless of their energy, should travel at the exact same speed and arrive at our telescopes simultaneously. But if spacetime is foamy, if it has a grainy, turbulent texture, that journey would not be so smooth. Think of it like two different-sized boats trying to cross a choppy sea. The smaller, more nimble boat, representing a low-energy photon, might navigate the tiny waves with relative ease, but a larger, heavier vessel, representing a high-energy photon, would be jostled and slowed more significantly by the same choppy water. In the context of the quantum foam, high-energy photons could interact more strongly with the microscopic fluctuations, causing them to lag ever so slightly behind their lower-energy counterparts. By meticulously timing the arrival of these photons after their billion-year journey, astronomers hope to catch the foam red-handed, revealing a tiny but crucial delay that betrays the universe's grainy foundation. Another subtle fingerprint involves polarization, the specific orientation of light waves as they travel. As light propagates through the seething foam, its polarization could be randomly twisted, a phenomenon known as birefringence. This would be like a clear, steady beam of light passing through a constantly shifting, frosted glass, its pure signal becoming slightly scrambled. The major obstacle is untangling this potential signal from all the other cosmic interference a photon encounters on its epic voyage. Magnetic fields, interstellar dust, and gravitational lensing can all mimic these effects. Isolating the unique signature of the quantum foam requires comparing data from multiple sources, from gamma-ray bursts to the ancient light of quasars, and pushing our instruments to their absolute limits of precision. Successfully identifying these faint whispers would do more than just confirm a theory. It would fundamentally reshape our understanding of reality, proving that the void itself is alive with a turbulent, microscopic dance. The hunt for these subtle fingerprints is already underway, pushing our instruments to their absolute limits. While we cannot build a galaxy-sized collider, we can use the universe itself as our laboratory. One of the most sensitive tools for this search is the laser interferometer, a device that splits a beam of light and measures how the two halves recombine. In a perfectly calm spacetime, the light waves would merge in a predictable pattern, but if they have traveled through a foamy vacuum, their journeys would be subtly different. The relentless churn of spacetime at the smallest scales would introduce a faint, statistical noise into the system, a constant whispering static superimposed on any signal. Future missions like the Laser Interferometer Space Antenna, or LISA, will search for this very effect by monitoring gravitational waves across millions of kilometers in the quiet of space. LISA lasers could detect the faint jitter caused by spacetime's granular texture, a background hiss from the quantum foam itself. Beyond gravity, we can look to the highest energy particles nature provides: cosmic rays, atomic nuclei traveling at nearly the speed of light, carry immense energy. If spacetime is grainy, these ultra-relativistic travelers should experience it. Their interactions with the foam could cause a phenomenon called dispersion, where different energy components of the particle's wave function travel at slightly different speeds. It would be like different colors of light separating as they pass through a prism, but here the prism is the vacuum of space. Detecting this spectral smear in cosmic rays would be a direct signature of the foam's turbulent nature. Even the oldest light in the universe holds a potential clue. The cosmic microwave background is the remnant glow of the Big Bang, a fossil imprint on the sky. Theorists suggest that the violent physics of the very early universe might have magnified the quantum foam's fluctuations, stretching them to cosmic proportions during a period of hyper-fast expansion called inflation. If so, the specific pattern of hot and cold spots in this ancient light could contain the amplified echo of spacetime's primordial graininess, a snapshot of the foam from the dawn of time. These experimental efforts represent the absolute cutting edge of fundamental physics. They are not just about confirming a theory, they are about learning to see the world with new eyes, to perceive the hidden turbulence beneath the apparent calm. Every unexplained blip of data, every subtle anomaly in a laser's path, brings us closer to answering one of existence's deepest questions. This microscopic chaos, if real, does not just reshape our understanding of space, it forces us to confront the very nature of time itself. The smooth, relentless flow of time we experience might be the ultimate illusion. Our classical view of time as a universal river flowing from past to future completely shatters at the Planck scale. Within the quantum foam, time itself may not be a fundamental background. Instead, it could be an emergent property, a collective consequence of the foam's ceaseless, turbulent dynamics. At this foundational level, time is not smooth. It is granular, composed of discrete, indivisible moments, each lasting a Planck instant. There is no continuous flow, only a rapid, probabilistic flickering between states, much like the individual frames of a film creating the illusion of motion. This radical idea directly challenges the singularity at the beginning of the Big Bang, a point where our equations break down and time seemingly begins. If time is foamy and granular, there is no true singularity, no true beginning in the classical sense. There is only a transition from a prior, highly quantum state where the very concepts of before and after lose their meaning. The foam's chaotic fluctuations could provide a natural resolution, suggesting the universe emerged from a timeless, foamy soup rather than a singular point of infinite density. This granular nature of time could also be the hidden engine behind one of quantum mechanics' great mysteries, decoherence. This is the process by which the weird, probabilistic quantum world gives way to the definite, classical world we observe. A particle exists in a blur of multiple possibilities until it is measured. Why does it choose one state? The jittering, grainy texture of time in the quantum foam could constantly interact with quantum systems, acting as a pervasive environment that continuously measures the universe, forcing probabilities to collapse into certainties. This perpetual interaction with the foamy vacuum may be what creates the definite past and the open future we perceive. This perspective even offers a tantalizing clue to the arrow of time, the reason why we remember the past but not the future. The relentless churn of the quantum foam, with its wormholes forming and virtual black holes evaporating, generates an inherent directionality. Each fluctuation is a tiny, irreversible event. The collective progression of countless such events throughout the cosmos could be the source of time's one-way street, linking the microscopic physics of the vacuum directly to the thermodynamic evolution of the entire universe. If time itself is a tapestry woven from this underlying chaos, then the very first moments of the cosmos must have been shaped by its primordial fury. The universe's first moments were a crucible of unimaginable energy, a place where the quantum foam was not a subtle whisper but the roaring heart of reality itself. In that searing heat, mere fractions of a second after the Big Bang, the energy densities were so immense that the distinction between the microscopic foam and the macroscopic cosmos vanished. The entire universe was compressed to a scale where its very fabric was this turbulent, chaotic sea. Every fluctuation, every virtual black hole and wormhole was not a fleeting ghost but a potent force capable of shaping cosmic destiny. This primordial foam is now theorized to be the original source of all structure. Its microscopic bumps and wrinkles, those random gravitational twists, were stretched to astronomical proportions during a period of hyper-fast expansion called inflation. Think of a tiny, random brushstroke on a microscopic canvas being blown up to cover an entire galaxy. The quantum foam provided the initial seeds, the minute variations in density that gravity would later sculpt into the vast cosmic web of galaxies, clusters, and superclusters we observe today. Some cosmologists go even further, proposing that the foam itself was the trigger for inflation. A particularly violent fluctuation in the spacetime fabric, perhaps the spontaneous creation of a specific kind of energy field, could have kicked off the universe's exponential growth spurt, setting the stage for everything that followed. This chaotic foundation also offers elegant solutions to long-standing cosmic puzzles. The horizon problem, which questions why opposite sides of the universe have the same temperature despite never being in contact, is resolved if the entire observable universe was once a tiny, interconnected region where the foamy network of wormholes allowed for instant thermal equilibrium. Similarly, the remarkable flatness of the cosmos could be a natural outcome of the foam's dynamics, its intricate structure ironing out any initial curvature. In essence, the early universe acts as the ultimate particle accelerator, a natural laboratory where the effects of the quantum foam were magnified to cosmic scales. Its fingerprints are potentially etched across the entire sky, hidden in the pattern of the cosmic microwave background, waiting for us to decode them. This profound connection between the smallest and largest scales leads to an even more mind-bending idea that the universe's entire history might be encoded on its outer surface, a concept known as the holographic principle. The holographic principle radically reimagines the fabric of reality, suggesting our three-dimensional universe might be a projection from a two-dimensional surface. This profound idea finds its roots in the study of black holes, where physicists discovered that all the information swallowed by a gravitational giant is not lost, but encoded on its event horizon, the point of no return. The entire cosmos could operate on a similar principle, where every star, every planet, and every one of us is akin to a holographic image emerging from a flat cosmic film. But what provides the pixels for this grand cosmic display? The answer may lie in the chaotic heart of the quantum foam. Its seething, turbulent structure is the perfect candidate for the underlying code. Each fleeting wormhole and every virtual black hole could represent a single bit of information, a 1 or a 0 in the universe's fundamental programming language. The foam's constant fluctuations are not random noise, but the active processing of data on a cosmic hard drive, with each Planck-sized region of spacetime storing a finite, minimal amount of information. This perspective elegantly bridges the worlds of gravity and quantum mechanics. The smooth, geometric force described by Einstein emerges from the collective behavior of countless information bits churning in the foam, while the probabilistic rules of the quantum world govern how that information is processed and exchanged. The foam becomes the essential intermediary, the translator between two seemingly incompatible descriptions of reality. This is not just a philosophical shift, it is a practical one that redefines the universe in terms of information theory. The most fundamental thing may not be energy or matter, but bits. The quantum foam, in this light, is the universe's raw, unfiltered data stream. This deep connection between information and spacetime forces us to look at the behavior of the universe's most basic constituents in a completely new way. The rules governing particles themselves might be written by this turbulent, informational foundation. This microscopic chaos reaches up to touch the very particles that constitute our world. The quantum foam is not a passive stage for particle physics. It is an active participant, its turbulent texture potentially altering how fundamental particles interact, scatter, and even decay. The perfectly smooth, featureless vacuum assumed by the standard model of particle physics may be an idealization. In reality, every electron and every quark moves through this seething sea of spacetime fluctuations. This journey is not without consequence. The foam's inherent graininess could act like a kind of cosmic friction, subtly modifying how particles collide. At immensely high energies, the kind present in the early universe or at the frontiers of our largest colliders, the chaotic foam might cause minute deviations in scattering cross-sections. These are the probabilities that govern whether particles bounce off each other or create something new in a collision. It would be as if you were trying to play a game of billiards on a table that was itself subtly vibrating and warping. The paths of the balls would be ever so slightly different from what you would predict on a perfectly flat, stable surface. One of the most profound potential effects is a violation of Lorentz invariance. This is a fundamental principle of Einstein's special relativity, which states that the laws of physics are the same for all observers moving at constant velocity. It is why the speed of light in a vacuum is a constant, universal speed limit. But if spacetime has a foamy, grainy structure, it provides a preferred frame of reference, a kind of underlying grid. A particle traveling at near light speed would effectively be plowing through this graininess, and a very high-energy particle might experience a slight drag, breaking the perfect symmetry Lorentz invariance demands. The most elusive particles, neutrinos, could be ideal messengers for this effect. These ghostly particles, which barely interact with matter, travel billions of light-years across the universe. If the foam slows down very high-energy neutrinos even a tiny amount compared to their lower-energy counterparts, our vast cosmic detectors might one day catch that telltale delay. Beyond motion, the foam's structure could influence the particles themselves through vacuum polarization. This is the idea that the empty space around a particle is actually a busy cloud of virtual particle pairs. A charged particle like an electron is constantly surrounded by a swarm of these fleeting virtual pairs, which effectively screen its charge, slightly altering how it interacts with other particles. The quantum foam, as the dynamic medium in which this all occurs, could modify this screening effect. It is conceivable that the very masses of particles and the strengths of their couplings, the forces that bind them together, are not immutable constants but are subtly shaped by their constant interaction with this turbulent foundation. This makes the search for foam's fingerprints a vital pursuit for the future of physics. Any confirmed deviation from the standard model's predictions could be a crack in the door, a glimpse into a deeper reality. The quantum foam might be the hiding place for phenomena predicted by theories like supersymmetry, which posits a shadow particle for every known particle, or it could provide evidence for the extra dimensions required by string theory. Particle accelerators are not just smashing protons, they are probing the texture of spacetime itself, hunting for the faint whispers of a chaotic, foamy vacuum. This tangible connection between the largest questions of cosmology and the smallest details of particle behavior inevitably leads us to a deeper, more personal inquiry. If the very stage of reality is a seething, probabilistic foam, what does that say about the nature of existence itself? This foundational chaos forces us to confront what reality truly is. Our deepest intuitions, built upon a world of solid objects and predictable cause and effect, shatter at the Planck scale. The quantum foam suggests that space and time are not the fundamental stage of the universe, but are themselves emergent phenomena, rising like a mist from a deeper, disordered substrate. This single idea unravels centuries of philosophical certainty. We are left to wonder if the cosmos is ultimately a continuous, flowing whole, or a digital reality built from discrete, grainy bits. The foam points strongly toward a pixelated universe where smoothness is a grand illusion of scale. This granular foundation is inherently probabilistic. The foam's turbulence means that at the most basic level, events are not predetermined by a chain of causes stretching back to the beginning. Instead, they are governed by chance and probability. This fundamental unpredictability filters up from the vacuum to influence everything, from the path of an electron to the evolution of a galaxy. If the bedrock of reality is fuzzy and uncertain, what does that say about our own choices? The ancient debate over free will versus determinism finds a new battlefield in the quantum foam. Our sense of agency may not be an illusion, but a complex expression of this underlying cosmic randomness. Consciousness itself, that most mysterious of phenomena, might be deeply intertwined with this quantum foundation. Some theorists propose that the brain's neural networks could be sensitive to these minute spacetime fluctuations, with our thoughts and awareness emerging from a dialogue with the foamy vacuum. This is highly speculative, yet it illustrates how profoundly this microscopic chaos could connect to our most intimate experience of being. Ultimately, the quantum foam imposes a humbling limit on human knowledge. There is a fundamental fuzziness we cannot overcome, a level of precision forever beyond our reach because the very fabric of measurement is flawed. Embracing this intrinsic uncertainty is not a surrender but a liberation. It invites a perspective where mystery is not a problem to be solved, but an essential feature of a living, breathing cosmos. These philosophical considerations are not a distraction from the science. They are what give the quest for quantum gravity its profound meaning, enriching the pursuit with a deeper wonder about our place in it all. This unpredictable, information-rich foundation may also hold the key to a technological revolution. The same probabilistic rules that govern the foam could be harnessed to build machines of unimaginable power. The strange rules that govern the quantum foam may soon power the next technological revolution. Superposition and entanglement, the very phenomena that create the foam's chaotic dance, are the same principles engineers are using to build quantum computers. In these machines, the basic unit of information is not a simple binary bit, but a quantum bit or qubit. A qubit can exist in a state of superposition, representing both a 1 and a 0 simultaneously, and multiple qubits can be entangled, their fates linked across the machine. This allows quantum computers to explore countless possibilities at once, solving problems that would take classical computers millennia. Yet, this incredible power comes with immense fragility. A qubit's delicate quantum state is easily destroyed by the slightest disturbance from the outside environment, a process called decoherence. And here is where the quantum foam enters the story in a very tangible way. The relentless churn of spacetime at the smallest scales could be the ultimate source of this disturbance. The microscopic fluctuations of the foam might introduce random errors into the qubits, as if the computer's circuitry were being subtly jostled by an invisible sea. This presents a fascinating paradox. The very phenomena that could disrupt quantum computers are the ones they might be uniquely suited to study. By constructing carefully controlled quantum simulations, scientists could create artificial environments that mimic the chaotic structure of the quantum foam. We could, in effect, run experiments on spacetime itself inside a quantum processor, testing how virtual wormholes form or how information scrambles in a black hole-like environment. This turns the machine from a mere calculator into a laboratory for fundamental physics. The connection runs even deeper. If spacetime is indeed a foamy network, some theories suggest it could be used for unprecedented forms of communication. Entangled particles might maintain their spooky connection through microscopic wormholes woven into the foam's fabric. While we are far from building a stable, traversable wormhole, understanding this geometric basis for entanglement could lead to revolutionary quantum networks where information is transmitted through the very structure of space. This profound feedback loop where quantum computers help us understand the foam and the foam inspires new quantum technologies highlights that this is not just abstract theorizing. It is a practical frontier. The race to build a stable quantum computer is, in a very real sense, a race to understand the turbulent foundation of our universe. As we push these machines to their limits, we are not just coding algorithms, we are probing the granular texture of reality. This granularity leaves its mark not only on the smallest particles, but also on the mightiest ripples in the cosmos. Gravitational waves carry more than just the echo of colliding black holes. They carry the faint imprint of the very space they have traveled through. These ripples in spacetime are the universe's most sensitive messengers, and as they propagate across cosmic distances, they must pass through the turbulent quantum foam. This journey is not perfectly smooth. The foam's grainy texture could subtly distort the waves, much like a clear sound wave becomes slightly warped after passing through a dense, choppy fluid. One potential distortion is dispersion, where different frequencies within the gravitational wave travel at slightly different speeds. In a perfectly classical universe, as Einstein predicted, all frequencies would move in lockstep. But if spacetime is foamy, the higher frequency components might lag ever so slightly behind, a tiny smear in the signal that betrays the vacuum's granular structure. Another telltale sign could be a random phase shift, a jitter in the wave's rhythm caused by constant interactions with the foam's fleeting wormholes and virtual black holes. Future generations of gravitational wave observatories, like the Laser Interferometer space antenna, will possess the exquisite sensitivity required to listen for this spacetime noise. It would manifest as a fundamental, irreducible static underlying all other signals, a constant hiss from the quantum foam itself. The most violent cosmic events provide an even richer laboratory. During the final furious moments of a black hole merger, spacetime is churned into a frenzy. At these extreme energies, the quantum foam is not a passive background, it becomes an active participant. Its dynamics could imprint a characteristic signature on the gravitational wave signal, a subtle deviation from what general relativity alone predicts. Perhaps the ring-down phase, where the newly formed black hole settles into a stable state, carries the fingerprint of the foam's microscopic turbulence. Decoding these effects requires more than just powerful telescopes. It demands sophisticated new models that incorporate the principles of quantum gravity, pushing our theoretical understanding to its absolute limits. This fusion of gravitational wave astronomy and quantum theory is transforming our quest, turning the cosmos into a direct testing ground for the fabric of reality. With this powerful new probe, we can now ask an even more profound question about the foam's influence, one that addresses the ultimate fate of the entire cosmos. The universe is not merely expanding, it is accelerating, and the quantum foam might be the hidden engine behind this cosmic speed-up. One compelling idea is that the vacuum energy of this foamy sea acts as a cosmological constant, a kind of repulsive gravity woven into the fabric of space itself. Picture a vast, invisible energy field, its power derived from the ceaseless creation and annihilation of virtual particles in the foam. This energy should, in theory, be driving the cosmos apart at an ever-increasing rate. Yet here we encounter one of the most profound puzzles in all of physics. When theorists calculate the expected strength of this vacuum energy, the number they get is catastrophically large. It suggests an expansion so violent that galaxies, stars, and even atoms could never have formed. The universe should have torn itself apart in its first moments. But our observations show a much weaker effect. This staggering mismatch between prediction and reality is the infamous cosmological constant problem, a glaring clue that our understanding of the quantum vacuum is incomplete. Perhaps the answer lies not in a static energy, but in the dynamic, evolving nature of the foam itself. As the universe expands and cools, the character of its microscopic turbulence might be changing. The frenetic bubbling of spacetime in the early cosmos could have gradually settled into a different, more subtle rhythm, one that only recently began to dominate the cosmic expansion. In this view, dark energy is not a mysterious substance, but a temporal echo of the foam's evolving geometry. Some models even suggest that the foam's intricate network of wormholes and fluctuations could generate effective repulsive gravity, a cosmic pressure emerging from the collective churn of spacetime's smallest parts. Resolving this puzzle is paramount. It forces us to ask whether the vacuum energy we measure is merely one possible outcome in a much vaster cosmic landscape. This line of thinking naturally opens the door to an even more staggering possibility, that our entire universe is just one bubble in an infinite, frothing multiverse. Our own universe might be just one bubble in a boundless, frothing ocean of reality. This staggering idea emerges directly from the behavior of the quantum foam, where its most violent fluctuations can do more than just warp spacetime. They can birth entirely new cosmic domains. In one compelling scenario known as the bubble universe model, a particularly energetic convulsion in the foam acts as a seed. Through a process called quantum tunneling, a speck of this false vacuum can tunnel through an energy barrier, inflating at a fantastic rate to become a full-fledged universe with its own unique physical laws. Our entire cosmos, with its specific constants and forces, could be the result of such a random, primordial event within the foam of a parent universe. This perspective transforms the foam from a backdrop into a cosmic nursery, its ceaseless turbulence generating an endless diversity of worlds. The connections do not stop at creation. The same transient wormholes that flicker within our local foam could, in theory, be threads stitching different universes together. These would not be tunnels you could travel through, but fundamental bridges in the multiverse's fabric. They might allow for a subtle exchange of quantum information between otherwise separate cosmic bubbles, a whisper across the vastness of meta-space. This provides a breathtaking answer to why our universe seems so finely tuned for life. If an infinite variety of universes exist, each with different rules, then it is no surprise we find ourselves in one where those rules allow for galaxies, stars, and planets to form. The quantum foam becomes the engine of this ultimate cosmic diversity, its random, creative churn ensuring that every possible reality gets its chance to exist. This profound link between the smallest scales and the grandest cosmic structures forces us to look at another of the universe's great mysteries in a new light, the spooky connection known as quantum entanglement. Einstein famously dismissed quantum entanglement as spooky action at a distance, a ghostly connection that defied any classical explanation. Yet this very spookiness might find its home in the chaotic heart of the quantum foam. The phenomenon where two particles remain linked across vast distances, instantly mirroring each other's states, could be physically woven into the fabric of spacetime itself. A revolutionary idea known as ER equals EPR proposes that every pair of entangled particles is connected by a microscopic wormhole threading through the foamy vacuum. In this view, the wormhole is the entanglement. It is not that the particles are communicating faster than light, but that they are not truly separate at all. A tiny bridge in the foamy substrate permanently links their fates. This provides a breathtakingly elegant geometric explanation for quantum weirdness, suggesting that the rules governing particles and the structure of gravity are deeply, fundamentally intertwined. The quantum foam becomes the universal translator, the dynamic medium where information and geometry become one. Exploring this relationship is more than a theoretical exercise. It forces us to reconsider the nature of separation and connection in the cosmos. If entanglement is a web of microscopic wormholes, then the universe at its most fundamental level is a deeply interconnected network, with the foam's ceaseless churn constantly reweaving the threads that bind one place to another. This profound unification points toward a resolution for one of physics' most vexing problems, the terrifying infinities that lurk at the center of black holes. The terrifying infinities at the heart of black holes and the Big Bang are not a sign of magic, but a signal that our physics is incomplete. A singularity is a point of infinite density where the elegant equations of general relativity simply break down and our understanding of reality grinds to a halt. It is the ultimate dead end in our cosmic map, yet quantum foam offers a breathtaking escape route from this mathematical prison. Its fundamental graininess means that space itself cannot be compressed into an infinitely small point. There is a smallest possible size, a final pixel of reality. This discrete structure acts like a cosmic cushion, preventing matter and energy from collapsing all the way to a true singularity. In the framework of loop quantum gravity, this leads to a spectacular possibility, a cosmic bounce. Instead of a Big Bang singularity, the universe could have been born from the collapse of a previous cosmos, a great rebound where the intense pressure of the quantum foam caused contraction to reverse into expansion. Our entire universe, in this view, could be one phase in an endless, cyclic dance of cosmic death and rebirth, all governed by the foam's resilient texture. Even within a black hole, the story changes. The crushing gravitational collapse at its center may not end in an infinitely dense point, but rather transition into a region of incredibly dense, foamy spacetime. The fleeting virtual black holes that naturally pop in and out of the vacuum could act as regulators, their chaotic dynamics preventing a permanent, singular state from ever forming. This resolution of the singularity problem is not just a mathematical nicety. It is a fundamental step toward a more complete story of cosmic evolution, one where the universe has no true beginning or end, only perpetual transformation. This profound shift in our understanding of reality's foundations has begun to ripple out from the halls of theoretical physics, influencing the very way we tell stories about our place in the cosmos. This profound shift in our cosmic story has begun to ripple far beyond the pages of physics journals. The quantum foam has seeped into the cultural consciousness, becoming a powerful symbol in science fiction and a source of artistic inspiration. Writers and filmmakers have seized upon its implications, crafting narratives where heroes navigate foamy spacetime to traverse the cosmos, or where reality itself can be reprogrammed at its most fundamental level. These stories, while fictional, capture a profound truth: the universe is far stranger and more wondrous than our everyday experience suggests. They use the foam as a metaphor for the deep interconnectedness of all things and the inherent uncertainty that lies at the heart of existence. This cultural resonance makes an abstract concept tangible, sparking curiosity in a new generation of potential scientists and philosophers. In classrooms and public lectures, educators have found the quantum foam to be an invaluable tool. It serves as a perfect gateway to discuss the limits of human intuition. We are wired to understand a world of solid objects and smooth surfaces, but the foam reveals that this is merely a convenient illusion. By introducing this radical idea, teachers can shatter classical preconceptions, opening minds to the beautiful, counterintuitive rules that govern the quantum and cosmological realms. It transforms physics from a set of equations into an ongoing adventure, a grand exploration of the very fabric of reality. This act of demystification is crucial. It builds a vital bridge between the esoteric world of theoretical research and the public's understanding of the universe. When people grasp that empty space is a seething, dynamic substance, their perspective on reality is forever altered. They develop a deeper appreciation for the scientific endeavor, not as a collection of settled facts, but as a living, breathing process of questioning and discovery. The widespread fascination with ideas like the quantum foam underscores a fundamental human desire to comprehend our place in the cosmos. It highlights the immense importance of communicating these cutting-edge ideas in a way that is both accurate and accessible, ensuring that the wonder of fundamental exploration is shared by all. The journey to understand this chaotic foundation is far from over, and its future promises to reshape our world in ways we are only beginning to envision. The next decade promises to transform our search for the universe's hidden grain from pure theory into observable science. A powerful, interdisciplinary effort is now underway, uniting cosmologists, particle physicists, and quantum information scientists in a common quest. Each field brings a unique lens to the problem, creating a triangulation strategy that could finally corner the elusive quantum foam. Upcoming missions will provide our most sensitive data yet. The James Webb Space Telescope, peering into the deepest reaches of space and time, will analyze the ancient light from the first galaxies with unprecedented clarity, searching for the subtle blurring and polarization shifts imprinted by a foamy spacetime. Meanwhile, the Laser Interferometer Space Antenna, or LISA, will listen for the faint hiss of gravitational wave static, the collective noise of countless microscopic spacetime fluctuations. On Earth, the approach is entirely different. Laboratories are using ultra-cold atoms and sophisticated quantum simulators to create controlled environments that mimic the chaotic structure of the quantum foam. By trapping atoms in laser grids and manipulating their quantum states, scientists can essentially build a tabletop model of spacetime's turbulent behavior, watching as foamy dynamics emerge from the interactions of thousands of artificial atoms. This is not just observation, it is recreation, allowing us to run experiments on the fabric of reality inside a machine the size of a room. The theoretical front is equally dynamic, with work focusing on refining the specific, testable predictions made by string theory, loop quantum gravity, and other models. How exactly should a gamma ray burst light be delayed? What is the precise statistical signature of foam-induced noise in a gravitational wave? These theories are also forging new connections to seemingly unrelated fields like condensed matter physics, where exotic materials exhibit emergent behaviors that eerily resemble the collective churn of a foamy vacuum. This convergence of tools and ideas means that for the first time, we are not just thinking about the quantum foam, we are building ways to touch it. The steady march of technological progress brings the once impossible into view, suggesting that within our lifetimes, we may finally hold direct evidence that the void is alive. This entire journey, from a theoretical spark to the brink of discovery, rests on a few profound insights that forever change how we see the cosmos. Our journey ends not with a final answer, but with a transformed perspective on reality itself. The quantum foam reveals a cosmos built not on stillness, but on a foundation of ceaseless creative turbulence. We have seen how this microscopic chaos shapes the very geometry of spacetime, potentially seeding the vast galaxies we see today and guiding the universe's accelerating expansion through the enigmatic force we call dark energy. Its intricate dance offers a geometric heart for quantum entanglement and provides a profound escape from the terrifying singularities that once marked the limits of our understanding. While we have yet to capture its fleeting fluctuations directly, the compelling indirect evidence and its sheer theoretical elegance make it an indispensable pillar in the quest for a unified theory of everything. This hidden turbulence does more than challenge our intuitions about empty space. It enriches our entire pursuit of knowledge, reminding us that mystery is not a barrier to be broken, but a horizon to be explored. I would love to hear which of these ideas resonated most deeply with you, so please share your reflections in the comments. If unraveling the cosmos layer by layer brings you wonder, subscribe to continue this exploration together. Thank you for venturing into the hidden heart of reality.